Hi everyone, what's up? Welcome back to my tutorial channel. It's Daniela here, and today we are going to do some practice. There's no lecture in this video. I'm going to give you just some review problems. And please keep in mind that these practice are just some core examples. In order to have the best practice, you need to work on more and more problems that relate to this topic. Alright, let's look at the first problems. Let S be the stock price after 1 year with the following distribution. Calculate a semi-variance. Here we got a random variable with 4 possible values of S, and we want to find semi-variance. So first we need to recall the formula for semi-variance. The semi-variance is calculated by sigma square SV, which is expected value of minimum between 0 and S subtract V whole thing square. Where mu here is just the mean of this stock price of this random variable. So in order to find semi-variance, we need to first find the mean. And how we find the mean for random variable is easy. We take its value of S times its probability and then add these value up. So mu here is 11 times 0.3 plus 14 times 0.1 plus 15.5 times 0.2 plus 17 times 0.4, and it should be 14.6. So the mean of this project is 14.6. Now if we follow the formula of semi-variance, we basically have to ignore the positive deviation and focus on the negative deviation. Here the first number is 11. 11 subtract 14.6 is negative 3.6, which is a negative deviation. So we are going to work on this deviation. Number 14. 14 subtract 14.6 is negative 0.6, which is a negative deviation. So we also can calculate based on this deviation. Number 3, 15.5 subtract 14.6 is a positive deviation. So we have to ignore this deviation. 17 subtract 14.6 is a positive deviation, is greater than 0, so we have to eliminate it. Now we focus on only two numbers, 11 and 14. So the semi-variance here is we take the deviation squared times its probability. For the first number, the deviation is the first deviation is 11 subtract 14.6. So we take that deviation squared times probability 0.3. Then for the second number, deviation is 14 subtract 14.6. We take it square and then times 0.1. We got 3.924. That is the semi-variance of this stock price after 1 year. So this problem is simple. We just have to follow the formula of semi-variance. Now, if we are given a random variable that have like infinite value of x, then what should we do? Here for problem number 2, we are given a similar problem with infinite value of x. Here we got the number of bonuses by a sales agent is distributed as a geometric random variable with probability distribution. P of x is equal to 0.75x times 0.25, where x here can be any number from 0 to infinity, and we take only natural number. So here the list of possible value of x is infinite. So we cannot use the last method in problem number 1. For this problem, we have to consider summation. Here the question asks for semi-variance. Of course, before you find semi-variance, you have to find the mean. But how do you find a mean for discrete random variables with infinite value of x? We are going to use some trick for summation. Here, by definition, mu is summation of x times p of x, where x go from 0 to infinity. And P of x here is 0.75x times 0.25. So we got the second summation here. Summation x from 0 to infinity of 0.25 times 0.75 to the x times x. Now 0.25 is just a constant number. We can go ahead and bring it outside of the summation. So we got the third summation. We got 0.25 times summation x go from 0 to infinity of 0.75 to the x times x. Now if you observe when x equal to 0, the product is 0, so we actually can eliminate the value 0. So this summation becomes summation of 0.75 to the x times x, where x go from 1 to infinity. So you go from 1 to infinity. So our question is, how do we deal with this summation? Whenever you have like summation go to infinity or integration go to infinity, then we have to use a little trick to modify the this side of the equation into a function of mu, so that we can withdraw mu later. Alright, so the trick for this is we are going to degrade the value of x. So imagine if you have 0.75 raised to x minus 1, then take this times x minus 1. You also have the same summation. The value doesn't change much, it's still the same. So that is our determination. And in order to appear x minus 1, we just have to derive it. So I'm going to derive the x factor here first and then the exponent. For the x factor here, I can just rewrite it as x minus 1 plus 1. X minus 1 plus 1. Alright. And here I noticed that 0.25 is in front of summation. I don't want to be confused with the constant. So I'm going to times both sides by 4 to get rid of this 0.25. So we got 4 mu is equal to summation of 0.75 to the x times x when x go from 1 to infinity. Now, I want to appear x minus 1. So I must separate them into two different summation. And I take x here is equal to x minus 1 plus 1. Then use distribution lower to separate the summation into two summations. So I have here two summation. The first summation is x from 1 to infinity of 0.75 to the x times x minus 1 plus summation of 0.75 to the x, where x go from 1 to infinity. And don't worry, the second summation is basic summation, right? This is a basic summation that we can find a value easily. For the first summation here, we can just try to appear x minus 1 at the exponent in order to show up another mu. So let's do it one by one. The second summation here, I rewrite it as the green summation here. And the first summation here, I rewrite it as 0.75 times the rest summation. You see, by factor out 0.75, the exponents from x will be degraded to x minus 1. And now we are going to deal with these two summation, the red and the green. The green one is easy. It's just summation of a to the x when x go from 1 to infinity, and it should be a over 1 minus a. So I got 0.75 over 1 minus 0.75, and this is just 3. That's for the green summation. Now for the red summation. This red summation, if you times 0.25, you basically have another mu. So this red summation is just mu over 0.25. And now we have a new equation of mu, and this is just a linear equation. We got 4 mu is equal to 3 mu plus 3. So mu is just 3. That's easy. So we have found out the mean of this distribution is 3. Right? Now we should do the last step. We have to compute semivariance. If you compare the value of x with 3, we see that there are only 3 values that below 3, 0, 1, and 2. So only 0, 1, and 2 will give negative deviation. So we should have to focus on these 3 numbers and ignore the rest. Alright, so semivariance here is the first deviation, 0 subtract 3 square times probability of 0. The second deviation, 1 subtract 3 square times probability 1. The last deviation, 2 subtract 3 whole square, then times probability 2. And we got 3.140625. That is the semi-variance. Now let's look at problem number 3. The following is the lowest 15 values of a sample of 100 weekly stock returns. Here we got a list of the lowest 15 values that we cut off from the list of 100 weekly stock returns. And the question asks you to find two things. The first one is estimate the 10% value at risk, and the second one is 10% tail value at risk of the weekly stock returns. Remember, the value at risk is just a fancy name of percentile. So this problem is just basically you have to find a percentile. So the first step, find a 10 percentile. Here we have the sample size 100, and the trick in IFM to find the 10% percentile is like increase the value of the sample size up 1. So 100 plus 1 is 101 times the probability, which is 0.1, because we are interested in 10% value at risk. So we got a number 10.1. So 10.1 here is a number between 10 and 11, which means that the value at risk should be between the value at the position 10 and the 11th position. The number at the position 10 is negative 0.3784, and the value at the 11th position is just negative 0.3755. So we question which number we should choose to be the value at risk. Well, technically, you can take any number between them. You can take negative 0.3784 or negative 0.3755 or any number between them. Those are acceptable. However, in order to have the most precise answer, we need to use a little technique, that is interpolation calculation. Because 10.1 here is not 10.5. It's not 10.9, it's not 10.7. You see, 10.1 is closer to 10, and it's between 10 and 11, but it's closer to 10. So the way to 10 is 0.1, and the way to 11 is 0.9. So we use interpolation. We take negative 0.3784 times 0.9 plus negative 0.3755 times 0.1. This is called interpolation approximation. So the most precise value for the value at risk should be negative 0.37811. That is the value at risk. Now, in order to find the 10% tail value at risk, we just have to find the average of all the possible value that below this value at risk. The value at risk is negative 0.37811. So we have to find out the list of all possible values that below this number. And we got 10 values from negative 0.7850 to negative 0.3784. We got the first 10 numbers on the list right here. So the tail value risk is just the average of them. We take these 10 numbers, add them together, divide by 10. And we got negative 0.48642. See that? So that's how we find the value risk and the tail value at risk of a specific probability. Okay, problem number 4. We are examining a new project. We expect to sell 9,000 units per year at 35 net cash flow apiece for the next 10 years. In other words, the annual operating cash flows is projected to be 35 times 9,000, which is $315,000. The appropriate effective interest rate is 16%, and the initial investment required to be $1,350,000. So what do we have in head, like after we read the whole context here? What do we understand this mean? Here, this is just a plan. This is our expectation that we expect to receive $315,000 in the next 10 years. Each year in the next 10 years. That means at time 1 year later, we expect to receive $315,000. 2 years later, we expect the same money and so on until 10 years. And the money that we pay today, the initial investment cost is 1,315,000. Interest rate is 16%. So if you look at the time value money, if you look at the time diagram, at time 0, you pay $1,350,000. At time 1, you receive $315,000. At time 2, you also receive $315,000, and so on to time 10. That is our expectation. So the first question, what is the base case net present value? The base case net present value is basically the net present value that is calculated based on our expectation, based on our plan. So here, it should be the present value of these 10 cash inflow and the negative 1,350,000 cash outflow, because we pay at time 0. So here the present value of 1,350,000 is negative 1,350,000 because that is the amount of money we pay at time 0. And at time 0, so we don't have to multiply with V. Now at time 1, we receive 9,000 times 35. So the present value of this money at time 1 is just 9,000 times 35 times V. And the present value of the second of the money at time 2 is 9,000 times 35 times V squared, and so on to V to the 10. So we got 315,000 times 1 minus V to the 10 over I, where I here is 0.16 and V is 1.16 to the negative 1. That's how we find the present value of the present value of the cash inflow and the cash outflow. And remember, what we pay, we have to use negative side. What we receive is positive side. So this is the net present value, 172,466.66. This is our expectation, that the net present value is 172,466.66. Now, part B. After the first years, the project can be sold for $950,000. At what level expected sale would be reasonable to abandon the project? That means the question asks for the break-even levels of the number of quantity that we should sell. That means we would have a break-even level, suppose like a few thousand, and if we got lower than that, we abandon the project. So here, let's say Q is the expected level of sales, the level of expected sales. So at time 1, we can sell it for $950,000, right? At time 1, we can sell it for $950,000. So the cash inflows from time 1 to time 10 should be 9,000 times Q. And because we are considered time 1, so the present value of the next 9,000 times Q of time 2 should be 9,000 times Q times V, and so on to V to the 9 instead of 10, because we are considered at time 1, not time 0. So we got 950,000 is equal to 315,000 times 1 minus V to the 9 over I. So Q here is 5,893. That means if we sell lower than 5,893 at time 1, we abandoned the project. If we got more than 5,893, then we continue the project. That is the break-even levels. And the question is, what will happen if we don't abandon the projects? That means after we know that we can sell the project to get 950,000, we basically just keep it. So that means like we will continue the project in 1 year and could forego the 950,000, and that could be used for something else. So at time 1, we have a choice of selling the project to get 950,000, but if we don't, then we lost 950,000 and we don't know what happened to our projects, but we know that we don't have 950,000 back. Now we consider a different situation. We continue on the last example. Suppose that it is likely that expected sale from year 2 and so on will be revised upward to 11,000 units if the first year is success, or a revised downwards to 4,000 units if the first year is not success. So here's the thing. After the first year, if you see that the project is success, then the expected sale will be revised to 11,000. Otherwise, it will be revised to 4,000. So this is a decision tree, right? We have two different cases. The annual sales of the first year is still 315,000. In addition, success and failure have the same change occur. That means 50%, 50%. So we got 50% change that we success and 50% that we got fail. So the question is, A, what is the net present value of the project if you cannot abandon the project? Before we solve this problem, why don't we call it base case NPV, but just NPV? Because this is the NPV calculated on one case that we cannot abandon the project. It's not the NPV on expectation at the beginning. So here, remember we have two outcomes, either success or fail. If success at time 1, then from time 2 and up, we raise the expected sale from year 2 and up to 11,000 units. So the value of the projects at time 1, if success is 11,000 times 35 times 1 minus v to the 9 over I. And we got 1,773,515.39. If we fail at time 1, then the value of the project should be 4,000 times 35 times 1 minus v to the 9 over I. We got 644,916.14. And because they have the same change occur, 50%, 50%. So the expected value of the project at the end of 1 year is the average of these two values. We take the average of 1,773,519 and 644,916. We got 1524217.77. So the net present value should be the present value of this money. But this money is at time 1, so you have to bring it back to time 0. At time 0, you pay 1,350,000, the initial investment. And at time 1, we expect to receive 1,524,217. So use time v for that amount to bring it back to time 0. So the net present value should be negative 36,019.17. This is the net present value of the project if you cannot abandon the project. Now, what is the net present value of the project if you can abandon the project? So here, if you can abandon the project, that means you can sell the project to get 950,000. So if you continue and if it's success, you got 1,773,519. But if you abandon projects, you got 950,000. So you have two choices here, and they have also the same change to occur. So the expected value project at the end of year 1 should be 50% times 1,773,519.39 plus 50% times 950,000 plus 315,000. 315,000 here come from the annual sale after the first year, because we are considered at the end of 1 year. So 315,000 is what we earn after the first years. So we got 1,676,759.70. And now in order to find the net present value, we have to bring these numbers back to time 0. And remember at time 0, we pay $1,350,000. And then at time 1, if we can abandon project, we have average 1,676,759.70. So the net present value here is negative 135,000 plus 1,676,759.70 times V. And we got 95,482.50. This is the net present value if you can abandon the project. And part C, what is the cost of option? The cost of option here is just like the gap. Here you see that if we cannot abandon the project, we got the net present value of negative 36,019.17. If we can abandon the project, then we got the net present value of 95 for 82.50. So that means the cost of option should be the gap between them. And the gap between them should be $131,501. That's the cost of option. It should the gap between two cases. The gap in net present value between two cases where we can not abandon the project or we can abandon the project. Alright, so I think that is it for today. Thanks so much for watching my video. I hope you guys enjoyed my video. See you next time. Bye bye.